Hello, and welcome to the 12th episode of Honest Discussions. I'm your host, Dr. Brandon Patterson, and today we're talking to Dr. Ori Gottlieb, who is a research professor at the Flatiron Institute. Ori is a really talented astrophysicist, and his models on the transition of neutron stars to magnetars is a really interesting model that predicts the existence of relativistic jets flying out of these neutron stars that are so strong that they can create gravitational waves. We discuss how gravitational waves are measured, what the problems are, or the potential concerns are with gravitational wave measurements, and some of the problems that may exist with Einsteinian physics as a whole. Really fascinating conversation with a really open-minded person that I thoroughly enjoyed, and as with all of these conversations, I learned a ton, and I'm sure you will too. So if you could, please just click, like, subscribe, share. Any little bit helps. We're still trying to get this channel off the ground, and it takes people like you listening to this to make that happen. So if you could do that, it'd be greatly appreciated. And with that, on with the show.
I see. Yeah, well, mine was far from being straight one. So my first experience with physics in general was in school, and it went really bad. I kind of thought my impression from school classes was that physics is essentially calculating how long it takes a ball to fall. And this is what physics is all about. And I have a lot of complaints to the education system. So they kind of,
if you want to, because I have plenty of complaints myself, but
yeah, so we can share it because mine are towards, I guess, the education system in Israel, where I grew up. So we can compare, I guess.
well, tell me, like, what were the issues?
I feel like teachers in general, they come and they don't come with passion, to try to trigger the curiosity of the kids, especially with science. And they come and they teach you what they need to teach you without trying to inspire you of how interesting and how important this stuff can be. So you don't get the broad picture of what it is all about, what physics is all about. Why do I need to study these topics? So for them, it's like it's just about pass the final exam, and there is nothing more than this. So I try to, yeah.
Do you think, though, that might have something to do with the fact that teachers are grossly underpaid for what they do, and that they don't have as much control over it as you might think, because part of schooling is to create workers? And if you're inspiring your workers to want to go look at the stars at night and investigate the universe, the last thing that they're going to want to do is go into a factory and live under fluorescent lights for their whole life.
I agree with that. And I think it is very much the truth. I am actually not sure, and I am curious to know how you see it in the States. But at least in Israel, the salaries are rather low for teachers. So the quality of teachers naturally will not be as high as you would like it to be, because people would like to get paid in the end of the day, and they can get paid. The good ones can get paid in other places better than in the education system. This is how you end up with, and their knowledge is rather limited. So even if you do have some type of, some curiosity, and you're asking questions beyond the topic that they're teaching, they may not have answers for you. So I certainly agree with you that if the salaries would be higher, probably the teachers would be better, and the next generation would be better too. So this type of I guess catch-22 is something that is part of the education system everywhere in the world to some extent.
Well, here in the States, the way that it works is depending on what area you live in, there are property taxes that then go towards funding the schools in the area. So this creates an immediate disparity in the United States, because if you live in an area where the average income is $500,000, which there are certain areas like Philadelphia, New York, Washington, D.C., so, you know, large cities, there are always these areas where the millionaires live here. And guess what? The millionaires' kids have great public schools because they pay all these property taxes and they can afford to pay for better teachers. But that's, you know, that's 1-2% of the U.S. Meanwhile, half the U.S. is living under what I consider to be poverty conditions, you know, $30,000, $35,000 a year or less income per person. And in those areas, and especially impoverished areas, it's way less than that. So they are getting the worst teachers. They have no money to get good teachers. And so they, of course, are going to be stuck in this deficit of having good teachers. And so, I mean, at a global scale, they're still underpaid. I mean, I think that this is clear. If we cared about our children and what they were going to do, teachers would be one of the highest paying positions that there could be. And there would be an incredible competition to be the good teacher, to be the one that can inspire kids to go do different things and whatnot. But that's not what we're living in. So
do you feel this type of competition exists in, say, the areas that you mentioned around New York, for instance?
Oh, for sure. For sure. But this would be no different, though, than trying to get into, let's just say, getting a faculty position, a tenure track, or even a tenured position at Caltech, or a tenured position at Harvard. I mean, not that big of a field, not that big of a group of people, and it's highly, highly competitive. But once again, you're talking about the 1%, the 2%, not talking about the average. And I don't know how to even begin to fix that problem other than to raise teacher salaries. I mean, and it doesn't just extend to public school. The same does happen in universities as well, in particular community colleges where, you know, people with PhDs are working for $50,000 a year. And right. I mean, we could even go there because I'm of the opinion we hand out way too many PhDs.
I agree with that too.
Do you agree with that?
Yeah, for sure. Yeah.
I mean, I felt trapped as a faculty member at UC Davis with some graduate students that, even at Penn State, the same way. Like, graduate students, they seem like they were going to work out, but then when you really get to that point where you're presenting your thesis proposal and whatnot, you realize, like, they just don't have it. They just don't have that thing. And unless you've done it, you don't know what it is. But there's a thing that you have, and it's a drive, and it's a competitiveness to be excellent, and all of those things. And they just don't have that thing. But the universities, because they're all about just statistics, they can't have lots of people dropping out of their PhD program, because then they show that, well, we don't have a high success rate, so why would you want to come here? Because we don't have a high success rate for granting PhDs. So they're just like, they do kind of force you to keep working with them and push them through, even though you're paying for them and even though they're not doing the work that you need them to do.
So you're saying that the admission bar is too low?
I think that not the admission bar, I think that the denial after the first or second year is too low.
I see.
Because I think there are lots of people that I've seen kids come in that aren't what you would think going to be great, and they hit their second and third year and they just blossom and they just become amazing. And you're like, oh, I would have never guessed. But you can also have this book smart person come in and that they have all the best test scores, and then they can't do a PCR, they can't do a simple measurement on an image, they can't do the easiest of things, even though they're wicked book smart, and they should be removed from the program, but you can't, or it's really hard. And then it also kind of looks bad on you as the faculty member that, well, you weren't able to make this person better, that they deserve a PhD. So it's a complicated thing, but I just think we hand out way too many of them, especially for the number of jobs that are available.
I agree 100% with everything, and I experienced all of this in a totally different area than yours, both in Israel and in the States. So I do think, and I agree with you, that there is no obvious correlation between success in studies, in courses, and in research. And I've seen both extremes as well. So I'm not sure what is the best way to handle that. Because the university cares about statistics and the advisor cares about statistics. And this might be the only evaluation that they can have.
Which is really unfortunate, because it's not the one that defines excellence. Even publications, I would argue, don't define excellence, because the greatest ideas are often stomped by the dogmatic community of whatever they're working in for years and years and years. And then, they always say, it's the joke, it's like they completely dismiss you, then they argue that it's impossible, and then when they have to accept it, it's like, well, but of course we always knew that all along. It's like this, this discontinuous thing. And there are many discoveries, especially in physics, where people were downtrodden for upwards of 20 years before their paper was published, and then ends up revolutionizing physics. But had we just given it a little less scrutiny, so that more people would have been interested in exploring those ideas, we would have been 20 years ahead of where we are.
Yeah, that's true.
Yeah, so it's hard, because the rebels and the groundbreakers are always going to be the ones that experience the hardest path.
I also feel like it's of the university's interest to take more graduate students to help with TA and to help with research, basically, for the advisor. So even though the advisor may understand and realize early on that this student is not having a future in the academia, they would still rather have the student doing all the dirty work for them, instead of letting them go.
But they should pay them then, all their salary. Then they should pay them, because when you're paying them out of a grant, that's money just thrown away.
Right. Yeah, but that we understand that this is hard to make it happen.
It is. But back to your story. So you had crappy physics teachers in Israel.
I had two crappy physics teachers. At some point, I decided that my physics classes would become football classes. So I just didn't even bother going to the class and just wanted to do something else. And I finished school understanding that physics is not a very interesting topic, in science in general, I can say. I was sort of attracted to computer science in high school. So I went and studied computer science as in my undergrad studies. Toward the end of my undergrad studies, I was forced to take one class in physics. This was classical mechanics, and it also came with a sort of an introduction to special relativity. And this is where the spark was enlightened, and I wanted to learn more. So
Einstein will get you.
yeah,
Einstein will get you.
exactly.
I mean, got me. I'll never forget reading, and I've said this many times already, but I will never forget reading the most recent Einstein biography that came out like 2004, 2005, something like this. And that just inspired me so much. I mean, that book was filled with notes and ideas, and I learned everything that I could about general relativity and thinking in relativistic terms. Part of the reason I want to talk to you. But
Yeah.
since then, like in looking at all the data especially the new data coming out, new telescopes and whatnot, brings up a lot of questions. And that's another reason I want to talk to you, because your studies are what keep me on the fence. The types of studies that you're doing in the areas that you're exploring are the ones that keep me on the fence to a certain degree. So can't wait to dig into it. So you got the Einstein spark, and that was it. It was just like, I have to go down this road and see where it goes.
It wasn't that straightforward, because at that point I wasn't even sure if I have it in me to succeed in physics, considering my very poor background in physics. And I was already kind of old, because in Israel you also have to do on the
Military.
army, right? And I was already like graduating, so I was like 26 at this point, and I was not sure if I am even good enough to do physics. And I was actually thinking, I started to read a lot of popular science literature, and I wasn't sure if I want to do physics or biology, but I did know that at this point, this is what is interesting for me to do, is to understand how our world works, rather than looking at computer science.
Nice. Well,
So,
but computer science can help you learn about the world too. I mean, without the computational power we have and the people doing computer science, all of the revolutions in biology would be gone.
I feel like computer science is a very powerful tool to use to study how nature is working, but I don't find like the theory of computer science very interesting. It's not very appealing to me. So this is why I decided that I don't want to pursue computer science, and I just registered to start a new undergrad bachelor degree in physics. And yeah, that was the beginning of my physics journey.
And I assume in the second time through undergrad, it was a cakewalk. My guess.
It was, at some point you feel like you're so tired of these exams and of these courses, because you already graduated. Why do I need all of that again, to go through this with all these young students and everything? But I told myself that it's gonna get much better once I start doing research, if I get to this point, and indeed it did. So I'm grateful for my or of 15 years ago, who pursued these hard times in completing another bachelor.
But here you are. I mean, you're at Northwestern, great university. Like, yeah,
So
you've done it.
Yeah, I mean, I actually just literally a couple of weeks ago started a new position here at New York in the Flatiron Institute. So I moved from Northwestern just in the summer.
Nice, an institute. I made the mistake. I could have gotten an institute job twice, and I turned them both down. And in hindsight, I realized if I had just went to an institute, I might still be in science, but maybe not. It's hard to say. So, what do you find, just personally, to be the most fascinating thing about the universe?
Wow, that's a big question.
Big question. Big question.
So, well, if I look at it like from a cosmological perspective, or from
your perspective, whatever that is.
Yeah. Well, there's so many questions, really. I'm actually thinking, in terms of cosmology, I would say that probably the biggest question would be, and this is not something that I study, I don't even know how to start studying it, is how our universe behaves as a whole. Basically, how many dimensions it has, how it started, what drives its acceleration, right? This dark energy that we don't understand. All of these questions of like the big cosmological questions, I think that these are very interesting questions that tells us where our universe stands in this multiverse or whatever we have around it, before it or after it.
Exactly. I think that, well, hopefully we'll come up with some ideas today. But I agree with you. You don't know where to begin, but in my opinion, the place to start is locally. So, can we even truly understand our own solar system? Because if you can understand that, then can we understand how that's related to the next solar system, and then start building our model out to the Milky Way galaxy. And I think that some of the problems that we have in cosmology today, and I'd love to hear your opinion, I think that some of the problems we have is putting the cart before the horse. We're taking some of these models and putting them into, these galactic size experiments, yet we still can't explain something as simple as, well, why are the outer planets much hotter than they should be?
Right. Yeah, so I guess these are different disciplines in astrophysics. So there is this cosmological perspective, which is we try to understand the universe, the early universe, and the behavior of the universe. And there is this discipline of I guess cosmological objects, where we try to understand the physics of how planets and dynamics and stars, and at least in astrophysics they seem to be somewhat unrelated, or at least they are not studied simultaneously. So they're independently studied, and I'm not sure. I do think that there is some sense to this, because the universe probably doesn't care much about what it contains, if you focus just on the behavior of the universe as a whole.
Or does it? Because there's a very fine structure to the universe, and you can see it in the cosmic web.
Right.
So that, to me, as a neuroscientist, argues that it actually cares a lot about its structure, because if it didn't care about its structure, it would literally be a homogeneous thing. No, it's very highly structured, and there are clearly rules that are maintaining that structure. So, and if it cares about its structure at that scale, then it likely, just like biology, it likely cares about the structure at every level, all the way down to the microscopic, which I'm sure we'll get into that, the division between GR and quantum mechanics. But that's kind of how I see it, from that. If we're not examining what is closest to us that we can measure the best and get the most information on, it does make it harder to translate local events to global events. And maybe that's why there's this division. And the same is true in the biological sciences, but that's also why there's a great number of biological scientists now arguing for multidisciplinary systems biological approaches. And that's to bring these expertises together, because maybe we're just missing it because we're not working together.
Yeah, I mean, at this point, as long as we don't really understand much of how the universe evolves, I think that every way to explore it is legit and could be useful for us to understand it. Either we go top down or bottom up. I think that both ways are definitely something to consider.
That's true, because you can definitely go either way. Like there are benefits, and there are benefits to going both ways, because you'll learn unique things for
Right.
sure.
Yeah, yeah. So yeah, I guess there are many analogies that can be drawn between biology and physics,
Oh, well,
cosmology especially.
biology is ruled by physics.
Right. No, but I'm saying like it feels to me, I always thought about it like the theory of evolution. I don't remember who said it, but like that nothing makes sense in biology unless in the light of evolution. So evolution can explain many things that otherwise would look very unclear or mysterious to us. And I feel like this is the holy grail of physics, right? To try to make sense of all this chaotic universe by having this simple equation that would be the equivalent of evolution in biology.
You
And
know what? And I wished I could support that statement, but I've done a lot of work in evolution, and my opinion is that most evolutionary posits are grossly overstated. It's grossly overstated how much we can actually take from comparing sequences, especially once the level of identity gets down below, 30-40%, then you don't know you're really looking at the same things. And you need look no farther than the fact that we still have not solved the structure problem for proteins. And here we are, how many years later? And they're like, oh no, Google, this Google thing, it just tells you the structure, it just spits it out. Malarkey. Okay. It can give you some good ideas, but it's also giving you what it's going to look like in a crystal. That is not what a protein looks like in a liquid moving system that has Brownian physics, that has, who knows, entanglement, who knows about quantum electrodynamics, who knows all the various physical functions that are impacting that structure in a liquid environment where it's not in a crystal. So, and there's so many things that have come out with evolution recently that where we're finding more and more human species that are not dated to the right times. And so I feel like the problems that biology suffers with evolution, something like the Big Bang suffers in physics, because there is so much that correlates with the theory of the Big Bang, but there's so much that doesn't. And it's, the stuff that doesn't kind of gets swept under the rug, and the stuff that does ends up on the cover of the New York Times. So part of this platform is trying to just put it out there as to what do we really know? And what should we be on the fence about? What should we be still looking at both sides of this question? Or maybe there's 5 sides to it. Who knows? So, this is why we're talking. And this is why we're going to talk about gravitational waves. So why don't you tell everyone what gravitational waves are, why we are looking at them, and what they could mean for us in your physics community.
so just like we look at light coming from stars in the universe, which is known as the electromagnetic emission, we can also look, so-called look in gravity. And this would be, instead of electromagnetic waves, it would be gravitational waves. So as you know, we have 4 forces in the universe. We have the nuclear forces, and we have gravity, and we have electromagnetism. So far, for thousands of years, humanity was looking in the sky, and all we saw was photons, particles of light coming from distant stars, and we were observing the universe through electromagnetic emission. And then in 2015, after an effort of a few decades, LIGO managed to observe for the first time the universe, not through electromagnetic emission, but for the first time in a different way through gravitational waves. And the way it works is that when we have massive objects in space, as these small objects accelerate, they produce gravitational waves. So we can think about space-time as sort of a fabric in space, and this fabric is dynamic. It's not static. So as a massive object is moving through this fabric and it's accelerating, then it creates ripples in the fabric. These ripples are known as gravity. So for instance, we on Earth are at the distance of about 150 million kilometers from the sun. And this distance is something that the photons, the particles of light, cover in about 8 minutes. So this 8 minutes is the time that it takes the photon to go from the sun to Earth, and this is why we see sun as it looked 8 minutes ago. Now, gravity waves, just like photons, they travel also at the speed of light. So that means that if the sun would disappear now, then what would happen is space-time around the sun would start to straighten up, and ripples will be created in space-time, and these ripples will start propagating in space-time in the speed of light and will reach Earth only after 8 minutes. So not only we will stop seeing the sun after 8 minutes, we will also stop feeling its gravity only after 8 minutes. So in 2015, what was observed in gravitational waves, the first detection was of two black holes that were in spiraling in a binary system. And as the black holes are accelerating towards the merger of the black hole, they create these ripples in space-time, and these ripples had to travel for a distance of more than a billion light years to get to Earth. And after about a billion years of wait, these waves reached the detector of LIGO, and we detected gravitational waves here on Earth. And the way it works in LIGO is that there is something called interferometer. So two beams of light are emitted from perpendicular directions, and then they are scattered through mirrors, and eventually they are supposed to reach the detector. Now, what happens when gravitational waves are propagating through Earth is that space-time, which is dynamic, is shrinking and expanding, just like sound waves in the air when they're reaching our ears. And then as the gravitational waves are propagating through Earth, what would happen is that one direction of these photons that are supposed to go through would expand, and another or shrink, and the other direction would remain the same because it will be perpendicular to the motion of the gravitational waves. As a result, the two photons will not reach the detector at the same time. There will be a slight delay of the two. And this delay can be as little as
femtoseconds, right?
Right, exactly.
Yeah.
So the sensitivity is really an amazing project, engineering project of the LIGO, the interferometer, which is sensitive to distances of the size of the proton.
Well, isn't it like the 1/1,000,000th of a proton?
It's 1/1,000,000th. So yeah, so it's about 10 to the 20 centimeters. So yeah, that would I'm not sure
roughly,
about the
it's
but
roughly
it's
there.
smaller than a proton. So so it's very sensitive, and these gravitational waves, you can imagine that after they travel for more than 1 billion years in space, they get to us after they're rather exhausted and they're very weak. But nevertheless, because of the high sensitivity of the detector, we managed to detect that, and we could infer from this very short signal, we could infer the masses, the distance, many properties of the system just from the signal by comparing it with the predictions of general relativity that was postulated by Einstein. And ever since, we have
you have said a lot there. Let's unpack it a little, just a little bit. And let's start with this, because this is a question that's been posed to me and I cannot answer it. So maybe you can answer it. So the question that was posed to me is, if gravity can only move at the speed of light, then we're experiencing gravity that was where the sun was 8 minutes ago. And if you use this idea of, space-time, and that there's a bending of space because of where the sun is, how is it that would not cause a slingshot effect because you were always moving to where the sun was 8 minutes ago? And in their mind, it would create this slingshot effect because you're always 8 minutes behind. So that would slowly but surely create this increased elliptical orbit, and it would slingshot whatever was orbiting around it out into space. And I don't know how to answer that, because it doesn't make sense per se, but I don't know how to argue that, well, we are moving to where the sun was 8 minutes ago and not come to that conclusion. Do you see what I'm saying?
I'm not sure when you're saying that Earth is moving to where the sun was 8 minutes ago.
Well, the gravity is coming from where it was 8 minutes ago.
Right.
So if it's a wave and it's directional, it's moving towards where the sun was 8 minutes ago. So then, so now it's 8 minutes behind. So I don't understand. I don't know how to answer that question, to say, because I don't have the background that you do. So
we can, well, I guess, yeah, that could be a little bit complicated. But I guess if we were to imagine the sun being static in the sun frame of reference, and neglect for a moment the small motion of the sun with respect to the center of mass of the solar system, then space-time would be static because the sun is not moving. So the curvature of space-time is not changing. So it's true that you don't really generate new gravitational waves in this sense, because the sun is static in this frame of reference, and the curvature of space-time is static. So you can imagine, as the Earth is just orbiting the sun on the same trajectory that does not change in time. Now, you can think about it as gravitational waves are constantly generated, so space-time is not changing, but there is gravity, but this gravity does not change in time. So this is what creates this static curvature of space-time. So Earth is just seeing the sun in the same place at all times. I'm not sure if that makes sense.
I'm not fully understanding it. I see what you say, and I can see how it works in a static model perfectly. But it's when you add the motion of the sun into it, which is real. I mean, the sun the motion of the sun with respect to the galaxy, or with respect to the center of mass of the solar system, or with respect to the center of mass of the solar system.
Right. So, I mean, these motions are very small. The center of mass of the solar system, in fact, is inside the sun, as far as I remember. So the sun will have these very small motions around the center of mass, and Earth is very far away. It's 150 million kilometers away. So As far as Earth is concerned, I would say that you can safely neglect, at least for zeroth order approximation, these small motions of the sun with respect to the center of mass of the solar system, and you just see a quasi-static space-time around the sun. So Earth can safely follow this trajectory in this static space-time.
Okay. I think that is a good answer from a relativistic perspective, for sure. Thank you for providing that.
It's always confusing to think about this stuff because of the different frames of reference.
So let's talk a little bit about the measurements and the crazy precise nature of these detectors that, we're measuring essentially 1/1,000,000th the diameter of a proton. So one of the important parts of it to me is that they pump the chamber into this hyper vacuum where I think the vacuum levels in the LIGO light chambers are like 16-fold lower than the vacuum of space. So if you've pumped out all of the material, what is the light even traveling on?
So so this question is having very interesting historical perspective of the ether. That was something that was favored by many scientists. I think I would say about 150 years ago, before the Michelson and Morley experiment, which also took place with this interferometer.
And however, there are many physicists that argue today against that experiment, but
I mean that might be true, but the idea of light needs to have some sort of medium to propagate in, just like air is propagating, sound waves are propagating in the air, and water is propagating in water. The question is what photons are essentially. Is it some disturbance of some medium, or what it is exactly? So 150 years ago, I think many people were sure that this is the ether that Michelson and Morley tried to find, and they found that there is no such thing. And I think now we understand that photons don't really need a medium. Photons, you can look at them as particles that are just going from one place to another. Alternatively, you can look at them as waves of light, which is a fundamental property of space-time. It's one of the four forces of space-time. So we don't need the medium for light to exist.
So light doesn't have any dipole moments. Photons don't have any dipole moments.
So photons, they don't. No. So so photons have polarization.
And then how do you get polarization without a medium to polarize in?
Without a medium to polarize it. So the medium is, if you want, is the electromagnetic field. So the universe is full of fields. So we have the gravitational field, we have the electromagnetic field, and we have other fields that we can talk about in particle physics. But the idea that that some waves do not need a medium is the idea that their field is a fundamental property of the universe. So in a sense, you can think of their medium is always there, right?
Right. I mean, that's undeniable. That experiment kind of proves that there's some media there that the photon can use to move through. No different than if you accept the Higgs field. Well, that's what the gravitational waves are moving through. So since you brought it up, I'm going to ask it. Could it be, because we have it pumped down to this incredibly low vacuum, is there any chance that some of the changes they see in these detectors are due to quantum vacuum energy fluctuations, which have been shown, that that's part of photons, or that a part of causing electrons to release photons. As a fairly new study, but I mean, if the quantum vacuum or the quantum vacuum energy can cause the emission of a photon from an electron, that seems to be quite a lot of energy, actually, if you think about it. So could there be any of these effects going on?
Well, it could be. We in fact can measure these quantum fluctuations in the vacuum through what is known to be Casimir effect, when we take two conductive plates and we put them close to each other, so we can actually measure the energy that is released. I am not an engineer, and I am definitely not an engineer who helped to build and construct LIGO. So I do not know how they take these effects into account. What I can tell you is that the measurements that we get in LIGO are, of course, there is a lot of noise. And the noise is not just from the vacuum field, it's also noise that we get just from, I don't know, trucks that are going on the road next to the interferometer. They also produce gravitational waves that are detected in LIGO. So there are many terrestrial sources that need to be filtered, and there are many filters that are working on the data that is generated by LIGO. And in the end of the day, after the magic, this black box that it goes through, we have very clear templates that we can compare with analytic and numerical models of gravitational waves from binary systems and see what are the properties that we can generate, and they work very, very well. I would say ridiculously well. So
from what standpoint they work ridiculously well for predicting, or what do they work ridiculously well for?
So so for instance, we can take theoretical models and we can calculate what would the signature, the spectrum of gravitational waves from a given binary system would look like in LIGO. And this is how we can infer the distance, the masses, and so on of this binary system. And then these templates can be compared with the data that is detected in LIGO, and this is how we can learn about the systems. So unless there is some conspiracy of the universe that is generating these templates, although the source is utterly different, I would say that we have a lot of confidence in these results and in the source that is generating these results. And of course, as you mentioned, there are many noises that need to be filtered out before we can go to the data.
Well, I want to get into your data now. We are going to come back to what we were just talking about after we talk about your work, because I really like your paper. And so let's just start from the top. It's like, what are relativistic jets? How are they created? And I guess you should probably just start with how and why stars collapse from a GR perspective.
Okay, yeah. So there are many points that you mentioned. So I guess the story begins as the star is running out of fuel. So like, I guess everything we know from our day-to-day life, nothing lasts forever. So the star is getting old, and it doesn't have any more energy to burn. So as long as the star is what is known to be in the main sequence, it's generating heat, and this keeps it stable against gravity that is trying to collapse it. Once the star is running out of this fuel, it starts to collapse into itself. And then eventually, if the star is massive enough, the gravitational force is so massive that the core of the star collapses to a black hole. And then around this black hole, there is a formation of a disk And this disk is something that we can imagine that it's formed as the angular momentum in the star. So as we know, the sun and all stars in the universe essentially are rotating. So as the gas is falling onto the black hole from the external layers of the star, it doesn't fall straight into the black hole, but it has some angular momentum. Exactly. So just like Earth is falling onto the sun, so this gas with this circular motion will form a disk around the black hole. It needs sufficient angular momentum in order not to fall into the black hole. But in these stars, at least this is the condition for the generation of the jets, you need to have enough angular momentum, so you form an accretion disk around the black hole. And many black holes in the universe, we know of different sizes, that they are accompanied by an accretion disk. And the reason why this disk is called accretion disk is because gas is accreted onto the black hole as it's reaching the black hole while it's viscously falling inside the disk. So as gas is falling into the disk, onto the black hole, what happens is that there is also magnetic field in this gas. So the star is magnetized. As we know, the sun is also full of magnetic fields. And these magnetic fields are also falling into the black hole with the gas. They are carried by
can I just interject one little thing?
Yeah.
That if there's a magnetic field, there's also an electrical field. And I think sometimes we forget this. So not only is there a magnetic field, but there's also a very strong electrical field there.
That is correct. Yes. So so there of course they are coming together. We have strong electric field, we have strong magnetic field, and as the electromagnetic field is falling onto the black hole, the following process is happening. So what happens is that we have magnetic field lines that are twisting with the rotation of the black hole. The black hole is itself spinning because it conserves the angular momentum of the core of the star.
Right.
So the black hole is spinning, and because of this effect of space-time that is dynamic, the spin of the black hole is basically spinning space-time. So space-time is also spinning. And this is something that could be somewhat counterintuitive. So space-time is spinning. The magnetic fields that are reaching the black hole are also forced to move with space-time around the black hole, and it forms these twists in the magnetic field. This generates a current of what we call jets or collimated outflows from the poles of the black hole. And these are energized by the rotational energy of the black hole. Basically, we extract rotational energy from the black hole and use it to launch these collimated outflows that we call jets.
And they're just filled with gas, and probably there's lots of cool physics actually going on in those jets, creating materials that or elements and materials that we may not even know about.
In fact, that's somewhat embarrassing to admit, but we are knowing about jets for many decades already in all scales, galactic jets to stellar jets. But we don't understand what the composition of these jets is. So I
mean, they do know that they're in part plasma, right? They are at least in part plasma.
So they are very much likely launched while they are magnetically dominated, so they are driven by plasma processes. However, because of their propagation in space through the collapsing star, we don't know what the end composition of these jets after finally they escape from the star is, whether they are baryon polluted, they are basically loaded with matter, or they still somehow manage to keep their high magnetization, or maybe neutrino, antineutrino annihilation is something from the disk that can contribute to the power of these jets. So we're still not exactly sure what the composition of these jets is.
Okay, thank you for letting me know that. That's actually really good little nugget of information.
Yeah. So there are many embarrassing facts for
I
us.
don't think it's embarrassing. I think expecting the humans in 2023 to fully understand the universe, I think expecting that is embarrassing. That's what I think.
I actually I very much agree with this statement. I think if anything, not understanding something is a good thing. It means that we have many things to understand and explore and remain humble. So
I
so
could
this,
not agree with that statement more,
yeah.
for sure. So we have these jets. Now, what makes them relativistic, and why are they generating gravitational waves?
Okay, so what makes them relativistic is a question of how much energy they have. And they have so
Okay.
much energy. They are, in fact, the most powerful phenomenon in the universe since the Big Bang. There is nothing in the universe more powerful than these jets.
Okay,
And
just so people know, if you had to put it in the terms of thermonuclear bombs,
oh wow,
how many thermonuclear bombs would it take to put 1 second of that energy out? Just roughly. I mean,
these numbers, they don't even mean anything to, I think, to people. They would be like trillions and trillions of these.
trillions upon trillions upon
Yeah,
trillions. Okay,
yeah.
I think that does actually resonate with.
Um, I can try another way. I can say, if you were to take the sun now and all the energy that the sun contains, you could probably okay, it's not as much. It's about 1% of all the energy ever generated, and including in the mass of the sun that the sun had over its course. And this is in 1 second. So if the jet is lasting for, I don't know, 10 seconds, you can almost get 10% of all the energy of the sun.
That it ever had and never will have. Yeah.
Right.
Yeah,
Uh,
that's crazy amount of energy.
that is crazy. And the reason why these jets get relativistic is because there is no other way for these jets to utilize this energy. They naturally accelerate to essentially the speed of light because they have just so much energy. And importantly,
But doesn't that create a real problem too? Because of you're pushing up against the Lorentz equation, and then that those things should be so ungodly massive, moving at those rates, that even with that much energy, it would be very difficult to move them. Like it's a catch-22 kinda.
Yeah, that's true. So we actually can place some constraints on how massive they can be because we know that they are relativistic and we know how much energy they have. And it turns out that their mass is probably not more than 0.01% of the solar mass. Or in other
Got
words,
you.
it's probably not more than about 100 Earth mass.
Yeah, so really actually quite small in galactic terms, really small
Yes,
in galactic
they're
terms.
relatively clean. Otherwise, they wouldn't manage to reach these relativistic velocities that we observe. Nevertheless, it's still a lot of mass, still a lot of energy. And what helps them to get to these velocities is their geometry, because as long as they're collimated, they can remain relativistic. If they would not be collimated, if they would be launched, say, quasi-isotropically, well, they would have to lift the entire star, the entire collapsing star. And this would, of course, be impossible for such jets because they themselves don't have enough energy to carry the entire star and reach relativistic velocities. They don't have this energy. So the fact that they can just drill a hole that is covering about maybe 1% of the surface area of the star, and just being collimated through this hole is something that helps them to reach these relativistic velocities.
And then so what you did is you made a model that it can tell us roughly what gravitational waves should look like and what their frequency should be coming out of those jets, correct?
Right. So It's actually it's a little bit more than this. So what we looked at is not just the gravitational waves generated by the jet, but the gravitational waves that are generated by the interaction of the jets with the star.
Okay.
So what we saw using numerical simulations is when we are following the propagation of the jet through the collapsing stellar envelope, the jet is shocking the stellar envelope in its head as it's moving forward, because there is a lot of material here. So you can think about it as a drill bit that is drilling through the wall. It will shock the material in the front, and this material will spill sideways and form this sort of hot material, hot debris that is forming around the direction of the drill bit. And this material is actually called, it's taken from biology, it's called a cocoon, because this is
You're coming into my next question. Yes. So what is the turbulent cocoon?
So it forms this this shocked stellar material. So this material was here lying in peace, although it was falling, and then the jet is hitting it. So the jet is transporting energy from the jet to this stellar material, heating it up. The stellar material with respect to the jet head propagation is spilling sideways, and it's enveloping the structure of the jet. So this is why it's called a cocoon. So it's highly turbulent because it's freshly shocked material that is just lying there around the jet, and is propagating with the jet. So the jet is carrying the cocoon with it. So the jet is not just a simple jet, but it's a jet that has the cocoon engulfing it. The two are propagating outside, and eventually they break out from the star and they start spilling out of the star. So this is the cocoon, this is the jet, and this is what we're thinking of the jet propagation looks like when it's going through the star.
Okay, so then why was the gravitational quadrupole, and this is something I didn't fully understand. I didn't understand why the gravitational quadrupole was so important to your model. So maybe you could explain what that is and why that's important to your model.
Right. So for detecting gravitational waves or for emission of gravitational waves, we need coherent emission of gravitational waves. We need coherent emission of gravitational waves, and on top of this, we also need the gravitational waves not to be emitted isotropically. The gravitational waves you can think about it as they will cancel each other out if they are emitted in an isotropic fashion. And this is why we cannot see gravitational waves from spherical explosions. Gravitational waves can only be emitted when there is a quadrupole in the gravitational field.
Got you. That makes sense. So you're saying that if a sphere explodes of any kind and it explodes equally in all directions, all of the gravitational waves will be interfering gravitational waves, and they'll all cancel each other out.
Exactly. You remember we were talking about you need the mass to accelerate in space-time in order to get gravitational waves. So if you have a spherical explosion, you don't really have any acceleration. If you want to think about your center of mass, it doesn't really accelerate anywhere. But when you have a quadrupole moment, you do have acceleration of, if you want to break it into center of mass. So this is how you can generate gravitational waves.
Okay. One more question about the model, because I think it's important, is why does the viewing angle matter?
Okay. So the viewing angle will actually tells you what you see. So let's think about two scenarios. One scenario is we're facing the jet in front of us. So the jet is coming from the screen towards us with the cocoon. What we would see from our point of view is a spherical explosion. We have no way to know what's happening in other directions. we would see an axisymmetric explosion from our point of view. And this will not generate or generate very weak gravitational field due to the small asymmetries in the projected structure that we see from our line of sight. However, if we would look at this same system from the side, what we would see is two pairs of jets that are propagating from the center of the picture, one to the right, one to the left. This will produce a quadrupole moment. And then we will have a very aspherical explosion that will generate strong gravitational waves that we will be able to observe. So this is why the gravitational waves are angle dependent, and they are expected to be much stronger when we are observing them off axis.
Okay, so here it is. Give us the big reveal. So what did your study show, and is somebody looking to verify your model?
So far, as I mentioned, LIGO only detected gravitational waves from mergers of compact objects. It could have been black hole merger, it could have been black hole neutron star merger, or a neutron star merger. But we were limited only to gravitational waves coming from mergers. This is still the case. However, we are looking forward to the next generation of gravitational waves.
Well, they did just claim that they can see the hum in the background of the universe, gravitational waves, which that one kind of, if what you're saying is true and everything that's spherical will cancel each other out, it's hard for me to put my head around that all of the things that are going on in the universe don't just destructively interfere with each other and pretty much cancel out most things. But anyways.
Right. Yeah. So at least the direct measurements of LIGO so far were limited to, there are of course other indications of what we could detect, or even some indirect observations of pulsar timing of maybe gravitational waves. But as for LIGO detections, we were limited to binary merges, and we're thinking already about the next generation. One of the immediate candidates would be supernova explosions. So supernova explosions are essentially the explosions of the stars that I described before, but without jets. And these explosions are very common in the universe. They are much more common than supernova with jets.
Betelgeuse is supposedly about to go.
Sorry?
Right? Betelgeuse is supposedly about ready to go, right?
Could happen soon. I would say maybe 100,000 years or so.
Maybe.
Maybe tomorrow. But supernova are very, very energetic, very common. So we had a good reason to put our trust into supernova as the first non-inspired gravitational wave source. The problem with supernova is that, as I mentioned before, they're highly spherical. They're not perfectly spherical, but they're spherical enough so the gravitational wave emission from supernova should be rather weak. To put it in other words, if the supernova doesn't happen within our own galaxy, in the Milky Way, the rate of which should be roughly 50, maybe 100 years per supernova, we will not be able to detect the gravitational waves coming from the supernova.
Because they'll just dissolve out until they get here. They'll run into too many other competing waves that ultimately will destroy the signal, more or less.
So the spherical explosion.
Yes, that's what I'm saying.
The spherical explosion is just going to have a very weak quadrupole moment. So it will be a phase cancellation in a sense of the gravitational waves. And therefore, we cannot detect them outside of our galaxy. Maybe we can detect them from the LMC and Magellanic clouds, but not further than this for sure. Now, with the jet, as we saw, there is a strong quadrupole moment, and the energy reservoir is similar to supernova, potentially even more than supernova. So that tells us that the gravitational waves expected from this type of events is substantially higher than the gravitational waves that we expect in supernova, and therefore we can detect them not just from our galaxy, but we can get to distances of hundreds, maybe hundreds is a little bit too optimistic, but tens of megaparsec away from us. So
And a megaparsec, just so people know, is what, 1,000,000 light years or 10,000 light years?
It's about 3 million light years.
3,000,000 light years. And
Right.
then how many megaparsecs were you talking?
We're talking, so I would say maybe 100 million light years.
Crazy.
Right. So yeah, I mean, this is what you get when you are studying the most powerful explosions in the universe. You can get very far. In fact, these jets, they generate what we know as gamma ray bursts, in short GRBs. These events can be seen as far as the observable universe. We can see them from any point in the universe. This is because they're just so ridiculously bright. So these gravitational waves generated by the cocoon and the jet will be detectable out to about 100 million light years. So the detection horizon is much farther than the detection horizon of supernova and gravitational waves.
And what kind of a frequency will these be? Will these be short frequency or long frequency?
So the jet, because of its very high velocity, will probably be in subhertz frequencies. The reason is that the jet is lasting observationally, we know, for between 10 to 100 seconds. So the corresponding frequency would be about tenths to a hundredth of hertz. This is outside of the frequency band that LIGO can detect, and this is why we don't expect the jet to be detected in LIGO. Potentially in space-based interferometers in the next decade, hopefully.
Which is coming, yeah. They're definitely putting the money into trying to figure this out. So
right. So this is one aspect, but the cocoon, on the other hand, is not relativistic as the jet. It's moving. I mean, it's still not very slow. It's moving, say, at 0.7 the speed of light or so. So it's what we call mildly relativistic, and that implies that the frequencies would be higher than that of the jets. I would say that the frequency of the cocoon, from what we find, is expected to be between 10 to about 100 hertz, which is within the frequency band that LIGO is detecting.
For sure, yeah.
So we may detect already in the next round of LIGO in a couple of years. This is what we know to be, to date at least, the brightest gravitational wave source from a non-binary system, from non-inspiral. So we have hope that this would be the first non-inspiral gravitational wave source to be detected in LIGO. And if we do not detect it in LIGO in a few years, then we expect the Cosmic Explorer in the United States and the Einstein telescope in Europe to be launched in about a decade, and be having, and they will have, I think, about an order of magnitude improvement in the sensitivity to the similar frequency bands that LIGO is sensitive to. So we will definitely detect numerous events of cocoon's power gravitational waves. So I would say that this should be the focus of the non-inspired gravitational waves in the next generation.
So word to the kids out there thinking about going into astrophysical modeling like Ori does here. There's a high likelihood that you'll make a model that the technology to test it might happen after you're retired or you're even dead. This is the reality.
It is the reality, yes. So although we are talking about telescopes that are supposed to be already in the mid-30s, which is not that far, at least not for my time scale, we never know. Sometimes it can take 3 times as long as the original plan, and I may not be around anymore. So, yeah.
Well, I want to go back to what we were discussing before and ask you one tough question. Then I want to ask you one interesting question, and then I want to ask you one fun question. So,
Good.
tough question. How do you reconcile the fact that it's not even a small number, that there is a fairly substantial number of black hole neutron star mergers that were predicted to be seen by LIGO, yet we cannot find them with our telescopes, in particular since the James Webb went up?
Okay, so when you say by our telescope, you mean not in gravitational waves, but by electromagnetic.
So we see the gravitational waves because of the way that the interferometer works. They can infer the exact direction in space of where this occurred. And then we take a telescope and we look in that area and we can't find it. And in particular, what I noticed from those is most of them are something that's roughly 2.5 solar masses coming together with something that's roughly 5 solar masses. And both of those numbers are also kind of on the edges, because 2.5 solar masses is kind of the upper limit of the neutron star, and 5 solar masses is kind of the lower limit of the black hole. So what do you make of that?
Okay, so let me just say that you mentioned the black hole neutron star mergers, but in fact, for neutron star mergers, we only detected one with electromagnetic counterparts. So same question could be asked for neutron star mergers. Where are the electromagnetic counterparts? So I would say this way. We don't understand what is, so okay, let's start from the beginning. So there are 2 electromagnetic counterparts that we expect to detect following the merger of these objects. One is coming from the jet or from the cocoon that I mentioned before, the gamma ray burst, or some emission from this cocoon that we detected in the only event with electromagnetic counterparts, the neutron star merger of GW 170817. The other type of counterparts that we expect is called a kilonova, and this is the radioactive decay of the heavy elements that are generated in the neutron star black hole or neutron star merger. This kilonova is supposed to be very bright, and hence the name kilonova. It's like 1,000 nova. So this type of electromagnetic counterparts are indeed expected, and this is a great question of where they are. So I think for the jet, I'm not too concerned, because as I mentioned, the jet is highly collimated. So chances are we're going to miss it. We're probably going to see jets in maybe 1 to a few tenths of events. So that's okay that we haven't seen it. I would be surprised. Actually, we ran some calculations on the only event that we detected, and we found that it would have been observed in electromagnetic emission from the jet or the cocoon only in about 1 to 7 events. So we're actually on par with the statistics.
Okay.
But as for the kilonova, which is an interesting question of where these kilonovae are, because they are rather spherical. So we should not be missing them because of some geometric effects. And then there, I guess one of the implications is that the mass of the ejecta from this merger is not as massive as we would like it to be, because the kilonova emission is proportional to the mass that is ejected from the system. The mass that is ejected is undergoing radioactive decay and is powering this kilonova. So if we haven't seen this kilonova, it stands to reason that it's just there is not enough mass. And why there is not enough mass? So in black hole neutron star mergers, the mass is really determined by a few factors. One factor would be the mass ratio that you mentioned of the black hole to the neutron star. The higher the mass ratio, the less mass will be there. And the reason is that if the black hole is much more massive than the neutron star, it will just swallow it as a whole. There will not be a lot of...
There'll be no explosion per se.
Exactly. So this could be one implication. As far as I know, the two black hole neutron star mergers that were detected had a mass ratio that is closer to 4, I think.
Right.
So,
and what I was discussing are things that are closer to 2, or
yeah,
even slightly below
exactly.
2, even some.
So exactly. So with 2, so we expect more mass to be ejected than brighter kilonova. Other factors that are important are the spin of the black hole. If the black hole is spinning fast, it can generate it can disrupt the neutron star stronger and leave more remnants outside of the black hole horizon. Whereas if the black hole is spinning slow, the neutron star will just merge with the black hole and not mass of ejecta will remain outside. So another important parameter is the black hole spin, which we currently think, based on analysis of gravitational wave, that most black holes in the universe are actually spinning slow, which might be a bad thing for kilonova observations.
Interesting. I was not aware of that.
Yeah.
Like, when you say slow, what's slow for a black hole?
So slow would be, so what we use a parameter we call dimensionless spin, which varies between 0 to 1. So 0 means that it's static, and 1 means that it's maximally rotating. Basically, this is the maximum angular momentum the black hole is allowed to have without
Which is
exceeding.
roughly, I mean, it's not light speed, but it's something relatively close to light speed.
Yeah, you can think of, like, if you're sitting on the horizon and you're spinning, you cannot surpass the speed of light. So 1 would be maximally spinning, and I would say that most black holes seem to have something like 0.1, which is
actually very slow.
Yes.
If it's only, not even a tenth the speed of light, that's pretty slow.
Exactly. And what simulations show us is that even for a mass ratio of 2, if you take 0.1 spin, you don't expect to have enough mass to generate the detectable kilonova.
Got you. Okay, that actually
this might be the reason, but
then how do they detect it? They're detecting it in the LIGO detector, but it's not enough to see it visually, or in the in the IR spectra or whatever. It's still, like, to my mind, you would still be able to see it even with what you're saying in IR, like, just from heat. You should be able to see it from heat.
You mean coming from where?
Coming from the merger.
Oh, so so there should be some emission from the disk. I guess this is where it can become optically thin for the photons to be able to diffuse out of the system. We do not think that this emission is strong enough, and importantly, it might be all these photons will be scattered in the ejecta that is supposedly producing the kilonova. Now, if there is no ejecta, as in the case of the slowly spinning black holes, the question is if there is even a disk, because most of the matter is just falling into the black hole. There will be nothing to emit radiation.
I got you. I understand your position. Okay. Yeah, so from that perspective, that's what could be going on.
Right. But I have to admit, it's not fully understood. And importantly, it doesn't solve the question of where are the neutron star kilonovae. Because there we don't care about the spin of a black hole. It could be.
I have my doubts about neutron stars in general. So I'll just leave that there. Okay. So here's an interesting question. What do you think of the new James Webb Telescope data showing that there are galaxies that appear to be older than the universe, and that the early universe appears to be populated by very large, very well-developed galaxies, which prior to this were predicted to just not exist?
I think it just tells us what we should have learned many times before, that we don't really understand things as we wish we would. And importantly, I think that we had we should have learned similar lessons from dark matter, We know that dark matter in the universe tells us that the formation of structure in the universe should have happened much before we see it observationally. So we know that the structure of the universe should have been, or the universe should have been more massive in the beginning than what we thought it would be. So these observations of JWST just strengthen this point that we need better understanding, and hopefully it will constrain better the models for dark matter. I think this is what could make it the most interesting implication of this observation of the beginning of the universe. So
I think that's a great answer.
yeah,
Although I personally think that extends to gravity as well. Like I said, for me personally, I'm on the fence because being an Einstein fan and understanding how it works, and I mean, I went as far as to learn the matrix math and all of that to just so that I would know that I know. You know what I mean? And once you know that you know, then you can also look at other things and kind of give them some credence, because for me, the whole dark matter thing is very difficult pill to swallow. Okay, I'm not swallowing the pill of dark stars. I'm not swallowing the pill because you can't, it's all just a theory and there's nothing experimentally to base it on.
you're not the only one. I think it's hard for everyone. Nobody likes to take things that we cannot see. There are indirect evidence for dark matter, but I don't think anyone feels very comfortable with dark matter.
Yeah, because I think that and I hate using this term, even though physicists love it, Occam's razor would say that we don't understand gravity. That's what Occam's razor would say, is that actually we just don't understand gravity, that there's something going on with gravity that we're not understanding. And because we don't understand that, we have these mass deficits that then we assign to dark matter.
So I mean, not just Occam's razor would say that. Jacob Milgram also said it, and he built a modified gravity model to overcome the need for dark matter. But so while it worked, actually, it was consistent with some some rotation curves of galaxies. It failed in other places. And the dark matter is just, I agree with you that in a sense it's like it's like a joker that you can use to fit everything that you need, but there is more than just one or two evidence for dark matter. They come from different independent places. So the model of dark matter so far works better than any other model. I don't think anyone feels comfortable with this, but it works, whereas other models don't at this point. So I don't think,
I look, I love that answer because I think that as long as the average physicist and the average astrophysicist and cosmologist, if the average one is saying, I still don't like dark matter, I have hope that we'll continue to look at things that could get rid of that as one of our models. However, I've also heard the argument that, well, it's not is it important to really know how it works, or do you just want to be able to get predictive answers? And if you want to get predictive answers, then it just use dark energy and dark matter, because you can get things that allow these predictions to occur. And I always sit on the fence on that one too, because it all depends on context. There are certain contexts where I won't care whether dark energy exists or not, because I need to get this answer, because the Earth is going to be hit by an asteroid and we need to understand this. But from a context of knowledge, what an awful answer. And from a context of knowledge, I reject it completely.
I'm certainly, I'm with you. I don't like this answer at all. I think this is what we're here for, right? If not for the big questions to answer, then I don't know what we're doing here. I don't like this answer.
I really agree with that. That's awesome. Okay, here's the fun question. If you had one wish, if I'm the genie, you had one wish, what would you use it on?
Oh, wow.
Only one. You only get one. Not doing the three. You get one.
Wow.
But could be anything. But really could be anything.
I would probably, wow, that's a question that I would have to think for a while. But if you tell me that I have to decide, it's I think probably um maybe being immortal, so
Wow.
I
So
can
that you
wait
could
to see all the
understand.
answers to everything.
Wow. Well, but you may be immortal because you don't know. Actually,
I used
energy
to,
can't be created or destroyed, and consciousness certainly has not been. Uh, uh, Consciousness is probably less understood than dark matter and dark energy, and
you know,
that's true.
you started with a question of what I think is the most interesting question in the universe. So I was deliberating between what I gave you and consciousness, and I I have to say that consciousness might be even more interesting, but it just feels to me like something that we cannot properly understand because we're it's but it's we are so biased by structure that
But
you know
you have to wonder if consciousness isn't, because it's irreducible. Is that the beginning? Is that really the beginning of everything? Because unlike everything else we've discussed today, there is a certain level of reduction that we can apply to it. Consciousness is completely irreducible. You
yeah.
cannot reduce it to some thing because so many, even just from a biological perspective, like people talk about, well, brain size and brain function is what really, carries consciousness. And I love telling this story. There was a guy in Britain in the early 1900s that had an iron rod go through his head.
Yeah.
And he was a worker. And when he survived, and the part of the reason he survived, and he was apparently a fairly normally functioning person. But when they took the iron rod out of his head and could look into his brain, he had a tiny thin layer of brain material around his skull, and most of his skull was empty. And yet he was a perfectly conscious human being.
But he changed, right? He became hostile to the environment, and he turned out to be a completely different person.
Yes.
The consciousness changed in a sense.
Yeah, it did. But the fact that he could be conscious at all when you don't have any brain matter.
Right.
Right.
Yeah.
So,
I must say that as you know, in quantum physics, there might be, so there is this I guess this dichotomy between the classic world and the quantum world, and it seems like this is also irreducible to some extent because
well, that's true
there
too.
is the quantum behavior, and our brain, in a sense, at least in the particle level, is working, is obeying the quantum physics, and then we have the classic level of the macroscopic structure of the brain, and I find a lot of analogies here, also with deterministic and non-deterministic. So
Completely, yes. And I have some people coming on where we're going to discuss the quantum nature of biology and how that might relate to consciousness. So I'll be sure
looking
and send you
forward
a link
to,
when we
yeah.
get that. Yeah. Ori, thank you so much for doing this. This was an awesome discussion. You gave me 10x what I expected. Like really fascinating stuff. I wish you all the best in your future work.
It was amazing to chat with you. I had the real pleasure.
Yes,
Thanks
me
for
as
inviting
well.
me.
All right. Well, I'll talk to you soon.
Okay, bye-bye.
All right. Bye-bye.